So we will learn a few things today, but at the beginning of the semester, we scheduled for test two on the 13th, right? But I realized that we have the fall break from the 13th to the 14th. So we will have to postpone that into the next class time, which is what, Tuesday, the 18th, I believe. Okay, so you have a few more days to prepare for the test. I know some of you are very well prepared. So that's why I want to discuss a little bit about the exercise number 2. Okay, so keep in mind that test 2 will cover everything after we have for test 1. So including say red light 3, and then we have also the uh, the sorting, right? So topological sort, and also the decision tree for any sorting algorithms. So those are the fundamental things we will cover. So looks at the comments I made and sent to each of you about your exercise number 2, right? So here I just want to mention one thing is about the decision tree for the heap sort. So that is where I found, a few things. So let me share the screen with you, and I will go through the solution. I think all of you should receive it by email, but anyway, I will go through it so you know how to correct the solution. Okay, so we start with a heap, right? Because if A1, A2, A3, A4 is not a heap, then the first thing we have to do is to build a heap. And building a heap will give you a bunch of different scenarios. For example, you have A1 at the root, right? The second scenario would be A2 at the root, etc. And for each of that heap, you would have to build a different decision tree, and it will make it very hard. So that's why I said that you need to build the decision tree for the heap A1, A2, A3, A4, right? So that said, you already have a heap, and because it's a heap, so we have a few constraints. For example, we have A1 is the biggest one, meaning that A1 greater than A2, A1 greater than A3, and A2 is greater than A4, right? So based upon that, we will build our decision tree. So obviously, the decision tree we have in that many of you have it correct by first comparing A2 and A4, right? Because the first step in sorting would be swapping the last element with the root. So meaning we swap A4 and A1, and then we remove A1 out of the tree, right? So that said, we will try to have A4 comparing with A2. So whether or not it's true, it cannot be true, right? Because we already have A2 is greater than A4, right? So that said, the branch for the true condition will never happen, right? For the false means that we have A2 now is the max value, right? So we want to find the max value. So the next thing we would compare A2 and A3 because the current max value is A2, right? So that said, if A2 is lesser than A3, meaning the condition is true, then you see here we have A3 is the max value, right? So that said, we swap A3 and A4. And now the next thing would be swapping the root with the second last guess value, meaning we swap it back again, right? So we have A4 and A2, right? Okay, so similarly, at every branch, if you can just draw out what would be the condition of the tree at this point, then you will understand what would be the next step for comparison, right? So here, by building this decision tree, you will have to understand the algorithm very well. Yeah. So you have to understand what will the algorithm do step by step. So that's why I give you this kind of exercise, so you will have to understand the algorithm, right? Not memorize it, but understand that. Okay, that is a common mistake. So that's why I want to bring this one up. Okay. Any question about the homework exercise? Okay, if you miss anything, then just redo it, following what I provided as comments for you. Okay, so hopefully you will understand all of the topics. For red black tree, most of you did very well, right? So we just have to follow the algorithm, and once we understand the algorithm, it's very easy to implement that. Okay, so that is for the first half of the semester. So after test 2, the exercises and the test will be, you have a problem. You have to design your algorithm and implement that. Okay, I will not ask you some details about how you do with one particular example, but I will give you a problem. You have to design your algorithm using the concept you learned in this class. So the second half, mostly we will pay more attention to dynamic programming, yeah, grid the algorithms, and also the, little bit about the digital coins we have for, say, the few weeks at the rest of the semester. Yeah? The last few weeks of the semester, we will pay more attention to that. Okay, and then the next thing is about the topological sort. As you know, in the lecture notes, I also posted another example for how to solve the problem, right? So the first algorithm we designed was based upon the depth first search, okay? And the second kind of algorithm I provided in the lecture notes, if you like, just follow that. But the only problem we have with that approach is that it's a little bit hard to prove that the algorithm is correct. You know that proving that an algorithm is correct is not simply implement that, run the program for one or two examples. No, it's not, right? Proving the algorithm is correct, we have to show that the algorithm or the program will be correct for all inputs. And there's no way to test if we simply write the program and test, okay? Because there are infinitely many inputs, and testing infinitely many possibilities is impossible, right? It takes forever, right? So that's why I like the DFS approach. And let me remind you again about how we prove that the topological sort is always correct, right? Like here we have a dark graph, and then by following the DFS and list the items with respect to the finishing time in descending order, then we follow all of the rules, right? So the idea was that for every edge u to v, we prove that, okay, whatever edge we have, the finishing time of u is always bigger than the finishing time of v, meaning on the list, u is always on the left of v, right? So there are three possibilities. Once we touch the edge, right? Okay. So the first thing was that u, when we touch this, right, we push it here, and now we have to consider all of the, say, adjacent vertices, right? So we have v. There are three possibilities, actually. If v is white, right? So meaning that v has not been touched before, right? Then we will push v in, color it gray, and then continue, meaning we will have to pop v out. At that time, we record the finishing time, right? And continue with the u, right? Continue with the u. So that said, finishing time of u is always bigger than finishing time of v, right? So the other condition is that what will happen if v is white? We just took care about that, right? V is gray and V is black. What does it mean with V is black? So we have U, right? We touch the edge, we have U. Now, we look for the V, which is an adjacent vertex of U. If V is black, we don't touch it anymore, right? So we will look for another adjacent vertex, meaning that V has been taken care of, right? So if V is already taken care of, what does it mean? We already have the finishing time, right? So it said finishing time of V is even smaller than the discovery time of U. In other words, the discovery time and finishing time of V would be from here to here, right? Before the discovery time of U. Hence, the finishing time of U is bigger than the finishing time of V, right? So if V is black, we are done. Why we are done? V is gray. What does it mean? So V is gray means that at the time we have U to V, meaning it can be something here. Now we have U, right? If V is gray, meaning that V is on the stack, right? So meaning that V is somewhere here. Okay. Is it possible? It's not possible because when we have V is gray, so it's more like this. The only way we can have V is gray is we have something like this. U to something, right? To V, right? And then let's say if you have the V here, if V is gray, let's say we can have a few possibilities, but when V is gray, meaning that we are talking about the V already, so it can be, say here, if we have V somewhere here, and then now we have the U, right? And now we have the U to V again, right? So that's said, this is W, right? Okay. So we may have some X. Yeah. So let's say if you have an X from V to X, right? And then from X to U, so that said, V is on the stack, right? And then after that, we may have X, and now we have U. And now if we have the add from U to V, right? Then V is gray because V is already on the stack. Right? But this one is not possible because if it's the possibility, right? Then let's say we have the X here, maybe one or two of them. But if it's the case, if V is gray, right? Then we have what we call a back edge. And this one is impossible, right? Because why is impossible? So if V is gray, it's what we are talking about, meaning V is on the stack before we add U. And now, because we have the add from U to V, right? So color of V is gray, and we say that this guy is impossible. Yes, right? Because it created a cycle. And for the topological sort, we have a dark, meaning that it's a directed cyclic, right? We have no cycle at all. So this one is impossible because if it is, then we have a cycle, right? So that's why for all possibility, we have whenever we have an edge from U to V, the finishing time of U is greater than the finishing time of V. Okay? In other words, U is always on the left of V on every list we have, right? So that is the correct list. Why we have the algorithm is correct. The second algorithm is it has the same complexity, right? Meaning that it's big O n squared at most, or more precisely, it's big O of the number of edges plus number of vertices. So usually the number of edges can be twice, the number of vertices square, right? So that's the biggest complexity would be big O n squared, where n is the number of vertices. But in the real world, the number of edges is very small, right? So that's why we always use this formula. And the second algorithm, I have it here. So the second algorithm is also simple, right? So that said, for example, we first we list all of the vertices that has 0 incoming edges, and then we add the first one into the list. For example, in this case, we have B, right? And then we remove all of the edges from B. So we have a new graph, basically we can keep the old graph and then update the number of incoming edges for every node, right? So the next thing we have here is either A or C, right? So we can add either A or C into the graph. For example, we add C, and after that we remove all of the outgoing edges from C, right? So, and then after that we can add A, right? After that we will add D, right? And then we can either have F or E, right? So we have F first and then E. So then it's the list that will follow all of the constraints, right? If you like, you can find a way to prove that this algorithm is correct. It's a little bit complicated, right? It's not easy. And in fact, I have not seen any proof, formal proof yet. So that's why I introduce here. If you are interested, try to prove it, right? It's correct. In contrast to the previous algorithm I showed you using the DFS, right? We have a formal proof. Okay, actually, we can prove that the algorithm is always correct. The second algorithm I showed you is simple, but would be nice if you can find a proof that the algorithm is correct. Okay. I believe that we can do that, but I have not had time to write down the proof yet. Okay. Of course, I will not give that question to you for the test. Okay, it's a little bit of a small research here, but encourage you if you are interested. Right? Okay, so that is what we learned so far, and everything from here back to when we have test 1 will be covered in test 2. Okay? The key point in this part of the class is that you learn some fundamental things like sorting, whether or not a sorting algorithm is good, not in terms of running time, we call time complexity, but also in terms of the space complexity, right? Now, here is what we have for the programs I posted on the programming training on DOM-JOS, right? I saw that two of you, Caleb and Jared Martin, you are doing very well there, right? But the problem that you try to solve a few times and you still have the error, right? So think about what kind of sorting algorithm did you use? Okay. Whether or not it consumes too many space. And remember that if you use the merge sort, they have to have the extra memory space, which is an array. And if the input they give too big, you will have problem, right? Because in that situation, the computer will not have enough continuous memory for that particular problem. So if you simply switch your sorting algorithm into a more efficient sorting algorithm in terms of space, you will be fine. Yeah. Okay. So try it. And also, by the way, I posted 3 more problems on the training. And after the test, let's say it depends on what day is convenient for all of us. So looks like Thursday is not a good day. So I can switch back to Tuesday from 5 p.m. But you just have to tell me that you will be able to attend Tuesday, a week after the test, on 18. Can you just time in? Okay, who else can attend the training on Tuesday? Okay, so that's fine, right? So we will have it. Yes, okay, 3 of you at least. Okay, because we have to prepare for Tuesday the 25th. Let me check. Yes, okay. We will try to have it from 5 to 6 p.m. Okay. All right, so now the next topic we will learn is about dynamic programming. So today I will try to give you some motivation, and we will have a simple problem to solve. So you know what is dynamic programming and what we can do with that. And keep in mind that dynamic programming is very, very popular and very, very efficient. So that's most of the algorithm in computational biology, bioinformatics are based upon, right? So if you want to know some advanced algorithm that has real-world applications, then dynamic program is one of them. It's a main thing there, okay? So let me give you some motivation first. Okay, so far you have learned quite a few of different ways to write an algorithm, right? So first is the top down using the loops, like for loops, while loop, in order to solve a problem, right? And then we have divide and conquer, meaning that we use recursive algorithm mentally, right? Divide a big problem into smaller one and conquer the smaller parts before combining the results, right? So we will see that the biggest problem or the biggest issue with divide and conquer is about the efficiency. Okay? The complexity is there, but we can analyze that because we already know how to analyze the complexity, right? But here is one example. It shows us how bad and divide and conquer algorithm can be. Okay. So one example is about how to calculate the combination, right? So for example, combination of k element from n is k from n minus 1 plus k minus 1 from n minus 1 elements, right? In that we have a combination of 1 from n is 1, combination of n from n is 1, right? Okay, so we can write a divide and conquer algorithm, right? So for example, we can write a recursive algorithm for solving this combination calculation problem, right? So for example, here, let me make it a little bit bigger. Page width. Okay, so that said, in order to compute the combination of 4 from 6, then we have to compute the combination of 3 from 5 and then 4 from 5, right? And add them up. And then for each of the smaller problem, we have to apply the recursive algorithm again, right? So looking at the tree we have, right? So every calculation is represented by a node on the calculation tree. What do you observe? What you can observe from here is that, for example, combination of 3 from 4, yeah? Com of 4, 3 is calculated again and again, right? And then if you look at com 3, 2 is recalculated multiple times, right? So that's it. When we have a recursive algorithm, the biggest problem we have is some computation will be repeated many, many times and it's useless, right? So we don't have to repeat the calculation because one calculation can give us a result. And if we can somehow use that result, then we don't have to recompute the, for example, com 3, 2 again and again, right? So that's why the divide concur algorithm, if we use recursive programming, some calculation will be repeated many, many times. And the next example will show you some very serious issue. Okay? Now, the next problem is related to, what can you tell me about the problem when I show you these two pictures? Is for computing the Fibonacci number, right? Fibonacci number is pretty simple, but it has many real-world applications. Right? In finance, right? In the real-world situation, like what we have here of the sunflower, right? Okay. Okay, so Fibonacci number is very simple. Fibonacci number of n is Fibonacci number of n minus 1 plus n minus 2, right? Now, if we write a recursive algorithm, it's very simple, right? Okay, just fifth n, right? If n is equal to 1, return 1, n equal to 2, return 1. Otherwise, return fifth of n minus 1 plus fifth of n minus 2. Easy, right? So you have a problem. Write a program to calculate any Fibonacci number. We can design a simple algorithm. But the question is that algorithm a good one? Obviously, it's not. Okay? Why? If we write our algorithm like this, right? Don't think that we have done our job. Okay. Actually, we should avoid this kind of algorithm as much as we can because it fails spectacular. Okay, so let's see here. The first algorithm and then the first Fibonacci number can be calculated real quick, right? So it's about 4 in a million of second, right? But if we look at, say here, the 51st Fibonacci number, it takes 60 seconds. Okay, it's quite a bit. And if we have the Fibonacci number of 70, what option will you choose? If you know that the 50th Fibonacci number will take 37 seconds, right? How long will it take for calculating the Fibonacci number at the 70th? Which number will you expect? Is it 37 seconds? 74? Actually, it's D. Okay. So that said, if we calculate, if we write a program like that with some very small inputs, that's fine. But we will show that the complexity of this algorithm, let me go back here. What is the complexity of this algorithm? It's an exercise for you, okay? So use the knowledge you already learned in this class, calculate the complexity, time complexity for this, okay? But what do you expect? A, B, C, D, or E? It should be E, right? Okay, so, but try it to see whether or not you have the complexity of this algorithm is exponential. And that said, we should not design our algorithm using recursive programming like this, okay? So that said, we need to find a better way. So a better way is what we call dynamic programming. In the previous example is a very simple example of how to use dynamic programming. Dynamic programming, the idea is that we will try to use the result of the small pieces for the calculation of the bigger problem, right? So instead of recalculate some parts of the data again and again, we will try to memorize or record the results of the small pieces and build the result of the bigger piece based upon the recorded data. Okay, so keep it simple. What should we do for the Fibonacci calculation? Okay. So remember that before we use the Fibonacci as a recursive algorithm, right? So now what can we do if we try to memorize the previous calculation and use the previous calculation for the calculation of the new Fibonacci number? Okay, I'll give you 2 minutes in order to think about what can we do in order to calculate the Fibonacci number. So perhaps I will go back to the design of the recursive algorithm. Okay, so here we have the Fibonacci number, that is a recursive one, right? How can we design an algorithm? Now, here you will see that the Fibonacci number will be calculated again and again many times, right? So let's say if we have 5 or 6, right? It will be the result of 5 of 5 plus 5 of 4, right? And then here will be fifth of 4 plus fifth of 3, right? And then here we have fifth of 3 plus fifth of 2. And then here we have fifth of 3 plus fifth of 2, right? Etc. And here we have, okay, fifth of 2 is 1, right? Okay, fifth of 3 will be fifth of 2. This one is the base case, right? Fifth of 1. And this one will be the base case again, right? But from here, you can see that fifth of 3 is recalculated multiple times, right? Okay, so similarly, if we have fifth of 600, some parts of the calculation tree will be repeated again and again, right? So that's why the recursive algorithm, even though it's easy to understand, easy to design, but it's not efficient, okay? So how can we design our algorithm? In that we make use of the previous results. Okay, so let's see, I will ask you, okay? Can you think about an algorithm in that we don't have to repeat the calculation again and again, okay? And hopefully the new algorithm will be better than the divide concur in terms of the complexity. Okay, I'll give you 2 minutes and please have a brainstorm about how can we deal with this situation. Okay, any idea? Okay, sounds good, right? But how can we do that? If we have the recursive algorithm, there's no way to avoid the repeated calculation because, for example, 5 or 6, we will call the Fibonacci number with 5 and then call Fibonacci number of 4, right? Meaning, if we have a recursive algorithm, there's no way to avoid. Okay? So that said, yeah, it's a good idea, but how about thinking of what we will do with one example, right? So let's say we want to calculate the Fibonacci number of here, 8 values, right? So we will try to store the previous results, right? So that said, again, here I will have the index from 1 to n, right? Let's say here I have the index from 1, 2, 3, 4, 5, 6, 7, 8. Now, we know that Fibonacci number of 1 is 1. Fibonacci number of 2 is 1, right? So the next one, I simply add the previous 2 values. Here we have 2, right? And then we go to the next. We don't have to repeat anything, but simply use the previous result, add them together, we have 3. Go to the next, add them, we have 5. Next, 8, right? And 13, right? And then we have 21. Okay? So that is the idea. So we will try to skip the values from the smallest one, continue until we have the Fibonacci number we need, right? Okay, so that said, we can design our algorithm like this. My fifth, we need to have an array and the number of elements, right? So here, I will simply have if n is 1, return 1, right? If n is 2, oops, return 1. Return 1, right? Okay, and then we will have the next calculation. So for I from 3 to n, right? Okay, AI will be assigned with AI minus 1 plus AI minus 2. And that's it, right? It's what I just did, right? So if n is 1, n is 2, and after that, we just calculate the next Fibonacci number, and then we are done. And after the follow, we return an, right? Okay, is that simple? It's not simpler than the recursive algorithm. However, this algorithm has the advantage of not repeat the calculation. For example, fig 3 will be repeated here and here and here again, right? So the good thing about this algorithm is avoiding the unnecessary repetition of some calculation, right? What is the complexity of this? Time complexity, okay? Time complexity here, I ask you to do at home is exponential. What is the complexity of this algorithm? when I ask you to do the complexity, you have to have here. Okay, how many steps? One, one. Okay, so here, how many steps? Big O N, very good. Okay, so here we have big O N. That is the much better algorithm, right? Okay, just count, right? And here you have, say, N minus, say, 3 to N, right? So you have N minus 2 plus 1, right? Here you have N minus 2, and return, take only one step, right? So that's it, the whole thing is big O N. Okay? But is there any disadvantage of this approach? One of the disadvantages is we need to have an array. Okay? And if we have, let's say if we have to calculate n is too big, then we may not have enough. But for the Fibonacci number, we never go beyond the memory we need. Right? So the disadvantage is that using this approach, we may require more memory space than the recursive approach. Yeah? That's why you see that nowadays, many software like Microsoft Windows or Linux or other programs, other software system, it requires more and more memory space. The reason for that is they require more memory space so their software can work faster. Okay? Faster in the sense that they use dynamic programming and they need more memory space. So it's a trade-off between time complexity and space needed. Okay, but keep in mind that nowadays we still need to have the recursive algorithms because sometimes we don't have enough memory space using the other approaches. Okay, so one thing I mentioned to you last time was about the operating system, right? Scheduling of processes. All right. So last time you already learned that sometimes we cannot use heap because heap is requiring too much of the memory space. So that's why nowadays the Linux, the new kernel from Linux, they use red black tree, meaning they use the pointers for building up the tree, the red black tree, in order to uh, say make use of small less number of memory space. That's why Linux is used not only on computer but also some small devices like watches. Right? You don't have a lot of memory space on small devices, and you still need to have an operating system on that. So that's why red black tree is very important nowadays. Okay. Okay, so that is about the motivation, right? So why we need to improve the recursive algorithms. Okay, now the next thing we will learn is, okay, is the assembly line scheduling. Yeah. So I will introduce this one, but we will come back to design the algorithm for this after we learn a few simpler algorithms. Okay. So assembly line scheduling is a real-world application, and it's used a lot. Okay, and you know that is producing cars and vehicles, some big applications. And that said, they need to find the fastest way to produce the cars so they can earn the benefits, right? Okay, so that said, for example, here you see that we have two assembly lines. Each assembly lines will have some stations, right? And at any time, some station will be busy. Some station will take longer time than the other ones. So the question is that when they have a new chassis to enter the assembly line, how should they send the chassis, whether or not going through only one assembly line or going through, say, one and the other, right? So finding the best way based upon the current status of the assembly line will be a real-world question, okay? So that said, the problem is not a fixed problem. They have to have the real-time application here. So when they have a new chassis to enter the lines, they have to find out what would be the best way. Best means the fastest way to finish assembling the car, right? So which way will be the best? So we will try to solve this problem by starting with some simpler problems first. So before we come back to this assembly line. Okay, so the simpler one is what we call the matrix chain multiplication. So I guess you know how to multiply two matrices, right? So I will remind you a little bit about that right now. But the problem is as follows. We have a sequence of matrices. For example, we have A1 to AN, and we have to multiply them. And you know that for multiplying the matrices, we can either multiply them A1 to A2 first, or A2 to A3 first. Right, let me give you one example here. So we will try to find out what do we need to do. Okay, so let's see, we have three matrices, right? So matrix 1 has, say, 2 rows, 4 columns, and then matrix 2 has 4 columns, 4 rows, 3 columns, and then matrix 3 has 3 rows and 5 columns. If we want to multiply these three matrices, we can first multiply the first one and the second, right? And then after that, the result we have multiplied with the third matrix, M1, M2, M3. That is the first way. The second way would be we multiply M2 and M3, and after that, we multiply M1 with the result. So we have two different ways because matrix multiplication has the associative property, right? So either multiply this one first or these two first, we have the same results. Okay? Of course, when we multiply two matrices, we have to match the number. Okay? The column, the number of column here has to be equal to the number of row here, right? So that said, we have many different ways to multiply a chain of matrices. Is it important? Is this problem important? Yes, it's very important. It's used for solving differential equation approximately, right? And in engineering, they have to multiply thousands of them, okay? Even more in order to find out the, say, approximation for some results of the differential equations, for example, right? So that's why it's a known, very important problem that we need to address. As a computer scientist, we have to design a very good algorithm for solving this problem. Okay? So why finding the best way for multiplying the matrices is important. So here is one example. Okay, so first, multiplying two matrices, we all know, right? So we need to have, say, cubic algorithm, right? So that said, every element we need to calculate on the result will be multiplying row I with column J, right? By multiply first element of row I with first element of row J on the second matrix, right? And accumulate them. Add with the second element of row I on the first matrix, multiply with the second element of column J, okay, accumulate all of them. So that's what we have for the cell at row I, column J of the resulting matrix. Okay. And we have to do that for every element of the resulting matrix. So that is what we have as a cubic algorithm. For every row I and every row J, we have to accumulate the values by multiplying the first and the second matrix together, right? Okay. So now, since we have many different ways to multiply a chain of matrices, if we multiply them differently, is there any issue with that? Yes. Okay. The biggest issue is that for some order, for example, if we multiply M1 with M2 first, sometimes it takes much longer time for doing so if we multiply M2 with M3 first. So here is one example. So if we have three matrices, A1, A2, and A3, with the number of rows and columns you see on the shared document, right? A1, you have 10 rows, 100 columns. A2, 100 rows, 5 columns. And A3, right? 5 times 50. If you multiply A1 with A2 first, and then after that multiply with A3, the total number of calculation or multiplication of the small values are 2500. But if you multiply A2 and A3 first, that number of calculation will jump to 50,000. Okay, so you can see here, it's 20 times slower if we do the calculation by multiplying A2 and A3 first. Okay, so that's why we are interested in finding the best way to multiply the matrices. Of course, when you have 3 matrices here, you have only 2 ways, right? You cannot multiply A1 with M1 with M3 first. No, we cannot, right? Because if you have a chain here, you can only multiply this and then multiply with the rest, or multiply this and multiply with the first, right? Okay, so we have only 2 ways. So we cannot have any other ways around. So how can we design an algorithm that will help us to find out what is the best way to multiply the matrices here? Okay, so that is the problem, right? So in general, if we have a chain of matrices, okay, A1 to AN, and each of the matrices has the number of row and column, and because when we multiply the matrices, we must have some constraints, like the number of columns of A1 has to be equal to the number of rows of A2, etc. Okay, so that is the constraints. Those are the constraints we have. Okay. All right. So another example here, if we have 4 matrices, A, B, C, and D, where the number of rows and columns are on the shared document, right? So if we multiply, in this situation, we have a few more possibilities. Okay, so let's see. First, we can multiply A with B first, and then multiply with C, and then multiply with D, right? So the total number of calculation or multiplication of elements is 20,700, right? Okay. The second way is multiply AB first and then CD, or vice versa, CD first and then AB, and multiply the results together. Then we have the total number of multiplication is 41,200, okay? More than twice, right? Okay, so, I mean, little bit about 2 times, right? So the third approach, the third way is multiply B and C, and then after that multiply with D, and then finally multiply A with the result. We have only 1,400 steps or small multiplication, right? So you see the difference, right? Okay. Of course, we have other ways as well, right? So we multiply C with D, and then multiply with B, and then multiply with A. Okay, so a few different ways. Okay, if we have 4 matrices. But the difference is obvious, right? So if we can find the optimal way to multiply the matrices, then the results will be produced in a much smaller number of time, right? And this is what we want to do. Okay. So in general, if we have a chain of matrices from AI to AJ, right? I can be 1 and J can be N, but in general, we can talk about a small chain of the big chain, right? In other words, if we have an arbitrary chain of matrices, so what are we looking for? We are looking for the best way, meaning that the number of multiplication is smallest. Okay. So what does it mean? It means that we will try to break the chain into two smaller parts. Okay. Let's say here, I will remove this and then we try to have more than 3. Smooth. Okay, so that said, if we have let me turn this one off. Okay, so if we have the matrix like this, M1, M2, M3, M4, and M5, right? So we want to find out the best way by looking at what would be the cost if I break the chain here at this point, meaning what would be the smaller value having the first part, the second part, and then multiply the results together. Yeah. So in general, if I have here Mi and Mj, right, then what we are looking for is the matrix chain from I to J is the mean for K from I plus 1, right? 2, if we bracket I, we will try to have it at this point, right? Okay, we can put it here, but the obvious way is here, right? So it's I plus 1 and then J, okay, of M, I, K plus M, K, J plus the smaller, when we have the left, the right, and the cost will multiply these two together, right? So the cost will be, say here, if we have I1, I2, let's say, rename it a little bit. I row, I column, right? Okay. Say 2 row, 2 column, right, etc. So the cost for multiply this one with this one will be the row times column times with column of the last, right? So it will be the cost for multiply the two parts together. And we will try to see if we break it here, break it here, break it here, break it here. Okay. We will try to break the sequence at every point and try to have the minimum value. And if it's the minimum value, then it will be the minimum number of steps we need for multiplying this chain. Okay, so that is the motivation. So I will stop here, but next time we will go into designing the algorithm, analyzing that, and then we'll try to have some example to see if we have a chain of matrices, how do we find the best way? Okay, So, any questions so far? Okay, so if we don't have any question, then I will stop here for today. Okay, have a good fun break.